What's up guys, it's me, Sir Ernest, and today we're going to solve problem 8.15 of Fowles and Cassiday 7th edition. The problem reads, two weights of mass m1 and m2 are tied to the ends of light inextensible cord. The cord passes over a pulley of radius a and moment of inertia I. Find the accelerations of the weights assuming that m1 is greater than m2 and ignoring the friction in the axle of the pulley. Just like any mechanical problem, let's identify first the forces acting on our object. So here for M1, we have the gravitational force Fg1, which is equal to M1g vector. For M2, there's also weight, and that is Fg2, which is equal to M2g vector. Aside from these two, there are two tensions. One is the tension acting on M1, T1, and the tension acting on M2, T2. Also on the pulley, the same tensions are applied on the rim, T1 and T2. Because M1 is greater than M2, so what will happen now is M1 will fall down and M2 will go up. Consequently, the pulley will rotate counterclockwise. The acceleration of M1 will be y double dot, and that is the same acceleration of M2 because of the fact that the cord is inextensible. So here we can see that M1 and M2 are undergoing translation while the pulley undergoes rotation. Hence, we will have three equations of motion. So let's start with translation of M1 and M2. So for M1, the equation of motion is written as T1 minus M1g, and this is equal to M1 times negative y double dot. Here, the negative sign indicates that M1 moves downward. Similarly, for M2, the equation of motion is T2 minus M2g, and this is equal to M2 times y double dot. Here, y double dot is positive because M2 is going upward. And combining the two, we now have T2 minus T1 minus M1 minus M2g, and this is equal to M1 plus M2 y double dots. So what I did here is I subtracted this equation from this equation. So that's why it's T2 minus T1. Now considering the rotation of the pulley, we now have the net torque acting on the pulley is equal to T1A minus T2A, and this is equal to I omega dot. This can now be rewritten as T1 minus T2 times A, and this is equal to I y double dot over A. So here we take note that y double dot is equal to A omega dot. So combining these two equations, we now have minus I y double dot over A squared minus M2 minus M1G is equal to M2 plus M1 y double dots. Or rewriting this, we have M2 plus M1 plus I over A squared y double dot equals M1 minus M2G. So therefore, this equation will give us the expression for y double dot as m1 minus m2 times g divided by m1 plus m2 plus I over a squared. So that's it. This is the acceleration of the weights, assuming that m1 is greater than m2 and ignoring the friction in the axle of the pulley. We can arrive at the same result using conservation of energy, which tells us that the time derivative of the total mechanical energy is equal to 0. So if we're going to apply this expression, you can arrive at the same result. And this is because we ignore friction in the problem. That's it. That's the solution to problem 8.15 of Fowles and Cassiday 7th edition. Thank you guys for watching. I hope you learned something today, and I will see you guys in the next video. Bye-bye.